Properties of curves, page 12. Consider this function, e to the x divided by x. Does the graph have any x or y intercepts? Well, remember to find a y-intercept. What you do is you put in x equals 0. In this case, x equals 0 is going to give us either 0 or 1 over 0. Uh-oh. 0 in the denominator? No. Instead of having a y-intercept, we're going to have an asymptote. We're going to have an asymptote at x equals 0. What about when y equals 0? To find the y equals 0, we set the function itself to 0, and then we see if there's any values of x which are going to give us 0 here. Well, e to the x itself can never equal 0. No matter how negative x gets, it's never going to be exactly 0. So no, there's no y-intercept either. So the answer is no. Discuss f of x as x approaches infinity and as x approaches negative infinity. Okay, so let's see. When f of x as x approaches positive infinity, it would be basically e. The top would be going to infinity at an exponential rate. The bottom would also be going to infinity, but less quickly because it's going at a linear rate. So this is not something you guys really know how to do yet, but this basically it's going to go to infinity. What about when x approaches negative infinity? What happens then? Then we're going to end up seeing e to the negative infinity over x, and the e to the negative infinity goes rapidly to 0, and so basically this is going to be 0 from the bottom because the x is going to be negative. Okay. Actually, the negative goes over here, right? Okay. All right. So that was B. Now let's see. Find and classify any stationary points for the function. Okay. So are there any stationary points for e to the x over x? To figure that out, how about if we use either the product rule or the quotient rule to take the derivative? Let's say that it's u. Well, let's do the product rule. So it's u to the e to the x, and we'll put v equals x to the negative 1, and so u dashed is also equal to u to the x, and v dashed is equal to negative x to the negative 2. So let's multiply that out. So we'll have u dashed e to the x times v, which is x to the negative 1, plus u, which is e to the x, times v dashed, which is negative x to the negative 2. Okay, and is this ever equal to 0? Let's rewrite it here. Oops, minus e to the x divided by x squared, and that is equal to 0. So when is this equal to 0? E to the x over x is equal to e to the x divided by x squared. We can cancel out the e to the x's, and then we end up with 1 over x equals 1 over x squared. We can cross multiply. We get x squared equals x. X equals 1. So yes, there is a critical point or a stationary point. It's at x equals 1. Then it says find and classify the stationary points. One of the things we can do to find the sign of the derivative function easier is if we put everything over a common denominator. So how about if we put this over the denominator x squared? So this one is going to be let's see, and we can factor out the e to the x too. So I have e to the x times x minus 1. You can check that and make sure that when you multiply it out, it ends up with what we had before. So looking at this, if we put in we're gonna make a sign diagram for C, and in the middle we're gonna have x equals 1, which is our critical point, right? Our stationary point. So if we put in a big positive number here, we're going to get a positive number out. If we put in a big negative number, we're going to have a negative number out. Okay, so we already know that what our derivative does going from left to right. D. Find the intervals where f of x is concave up and concave down. Here we need to take the second derivative. Okay, and let's see. How about if we take the second derivative of that? It's a little bit easier, I think. So we're going to have the derivative of e to the x over x. Hey, what do you know? The derivative of e to the x over x, that would be the same as the original function, right? And we already know what the derivative of that is. It's that. So part of our derivative is going to be of the first term, which is the function itself, right? So the part of the derivative is going to be e to the x over x minus e to the x squared. And then we need to find the derivative of this second part. So that would be, we could treat it as negative e to the x to the negative 2. So that would be, we would use the product rule, and we'd have e to the x times negative 2 x to the negative 3. And then we would also have e to the x to the negative 2, and it would be minus also. So we're going to combine this, which is for the first term, this, which is for the first term, and we're going to combine that with this part, or I'm sorry, this part, which is for the second term. And we'll put that all that together in a big one big equation. And if we do that, we can see that we are going to be able to cancel out this and this. Oh no. So now I've taken this part and I've combined the like terms, and I get that. And now I'm going to put them all over a common denominator of x cubed. And I'll factor out the e to the x also, and I'll get 1 minus, x squared minus 2x plus 2. And since I'm figuring out when it's concave up, concave down, the first step is figure out when there are stationary points or critical points. We're going to set it equal to 0, and then we can see that if we factor, and if you check the discriminant here, you can see that there are actually no real roots for this. So there are no zeros for this equation. So there is, it's never 0. One interesting thing is that obviously x cannot be 0, right? So we do know that if we drew a sign diagram, we would put an asymptote at x equals 0, right? What about big positive numbers? Big positive numbers would make a positive number, right? Because a big positive number would make this very, very positive, a big positive number, and the rest of it wouldn't be able to overcome that. So that would be positive. And on the other side of it, if you put a big negative number, same thing happens. When you put a big negative number in there, it would just become a big positive number, and then the bottom would be negative, so you'd have a negative number. Okay, so the concavity is the critical point would be 0, although it's an asymptote. On one side, it's going to be concave up, and the other side is going to be concave down. So now it says to sketch the graph showing all important features, and so let's see, what is the point, what is the value of the function at for example, we know there's an asymptote at x equals 0 there, okay? But we also know that there is a critical point at x equals 1. At x equals 1, the function itself is equal to e over 1, which is going to be about 2.7, so it's right there. And the slope to the right of 1 is going to be positive, so it's going to go up. And to the left of 1, it's negative, so it's going to go down like that. But there's an asymptote, so we know that it goes up like that. And then if we look at the concavity here, we know that up to the right of 0, it's positive, and to the left of 0, it's negative. So, but it's funny because like the left side has no gradient 0 points. So there's no horizontal gradients here. So it has to look like this because it has to approach the asymptote, and it never curves down, because if it curved down, there would be a horizontal tangent here, and we know there isn't one. So we know that it's going to look something like this. Okay? So that's a pretty hairy looking function. Then it says, find the equation of the tangent to this line at a point where x equals -1. So it would be about there, right? I'm not going to use that same color. Okay, the tangent line is about like that, okay, at x equals -1. So how do we find that? Well, first of all, since we want the tangent line at x equals -1, we write down the function, or the equation for gradient intercept form, right? And then we know that the slope is going to be, we're going to use the gradient function, and the gradient function is here. Okay, we use that gradient function to find the value at x equals -1. So to do that, we're just going to substitute -1 in for both of these. So we're going to have e to the -1 over -1 minus e to the -1 divided by -1 squared, which is 1. So basically you have negative e to the -1 minus e to the -1, which is -2 e to the -1. Okay, and so that is the slope of this green line. Okay, that is the slope. And we're going to put the slope down here, right? Now what about x1 and y1? So x1 is easy, right? Because we already know that the x point is -1. To find y1, we need to put -1 into the original function. So if we put an x equals -1 into the original function, we're going to get e to the -1 divided by -1, so it would be negative e to the -1. So that would be our y point. So it would be y plus e to the -1 would be the y point. The m point would be -2 e to the -1. And then we would have x minus a -1. So, yeah. Okay, so that is the equation for the tangent line right there. Alright. Number 1. Using the graphs y equals f of x below, sketch the graphs y equals f dashed and y equals f double dashed. Show clearly the axis intercepts and turning points. Okay, so we'll basically just, use these critical points right here, and I am going to sketch a graph of f dashed. So, and then I'll sketch a graph of f dash dashed, and I will do that in blue. Okay, so you can see that for this function here, it is going down until it gets to this point here, and then it goes up after that. So f dashed for this function is going to be positive, or it's going to be negative, and then when it gets to here, it's going to become positive. So actually, and it's a parabola, the derivative is a line. So it's going to look kind of like this. It's going to be negative slope until it gets to here, and then it's going to be positive slope. Okay? And so that's f dash. What about f double dash? F double dash, you're going to have, if you take the second derivative, here it's just going to be a horizontal line at y equals 0. Because there's, this is just, well, not at y equals 0. It's going to be a horizontal line at some positive point. Like it's going to look like that. Okay. What about b? So for b, I'm going to draw again my critical points here. Okay. And you'll be able to see that when you take the derivative of this, you got a rising curve here until you get to this point here. Right? And then you got a curve that's going down until you get to here. So let me draw my other axes here for the f dash. And I'll go back to blue again. Okay, so I got a positive slope, and then until it gets to here, and then it becomes negative for a while until it gets to here, and then it becomes positive again. It's a parabola. Okay. All right, and then if I take the derivative again, then it's going to be a linear curve, and it's going to be a linear equation, and it's going to be positive starting at this point, and it's going to be negative to the left of that, right? Because here it's going down, and here it's going up. Okay, this should remind you of what we did during the investigation. Here we got let's see. So here we're going to say, okay, it's a positive slope until it gets to here. So, and then it's going to be negative for a while, and then it's going to be positive again. So again, we have another parabola. And then if we take another derivative, then it would be another, let's see, this is the 0 point here. Okay? And let's mark where all these intercepts and stuff are. So this intercept would be at halfway between -2 and 4, which would be 1. So this would be at 1. Okay? And like this one here is at 0. Okay? And the intercept here is it's probably like at -1 and 1. And here it would, this point here, this would be at probably about 1.5 or something. Okay, and then this starts to go up again is 3. Okay, and then this point here would be halfway in between. Okay. Number 2. For the graphs below, sketch a graph of what? All right, the graphs below are f dash. They're gradient curves. Sketch a graph which would be the original function which corresponds to these. So now we're going to do backwards. What we did here was we took the function and then we found the derivative and the second derivative. Here they give us the first derivative, and now we're going to try to find the original function. The best way to do this is look at, like, so this is a positive slope, this is a negative slope, and this is a negative slope. At 2 points, it becomes flat, which is here and here. Okay? So let's try to follow what they're doing here. So first it says, okay, positive slope, so we're going up, we're going up, we're going up. Then it's flat, and then it's negative slope. And then it's flat, and then it's negative slope again. Okay? So basically it's going to look like, okay, it's flat here, and then it's negative slope, and then like here it's also negative slope, right? And then it's flat here, and then it's positive slope. So it kind of looks like this. So there's it's flat here and here, but it basically looks like that, right? Goes up. It gets to this flat place, it goes down, but then it turns flat again, then goes down again. Okay. So these are the stationary points here and here, and points of inflection would be here. Okay? Alright, now let's do it for this parabola here. So these would be the points where interesting things would happen. So like first it's a negative slope, and then it flattens out, right? And then it's a positive slope, and then there's a inflection here, and then here it's flat again, and then it's a negative slope. So it looks kind of like that. Okay? And so here are the stationary points, and here is the inflection point. That's it for the last page.